Network elements, nodes, such as switches and routers, are used to help computers or devices communicate. In order to understand their operation, a bigger picture is required, and that is how the TCP/IP protocols work. Unfortunately, that is a big topic and requires a lot of reading. The book probably is like 1,000 pages long, but we can squeeze that in a little bit of a discussion here and put stuff in a nutshell. So in my blog, ciscoeasyblogspot.com, years back, I wrote a little bit of gist of what it takes for computers to communicate. And the two topics that I recommend familiarizing with are basically the encapsulation, de-encapsulation process, as well as TCP/IP traffic flow. Let's focus on encapsulation and de-encapsulation, which is basically wrapping around something in a header. If I go here, what I'm gonna basically quickly go through. So this is a TCP/IP protocol stack application, layer 7 through 5, transport layer. We have two protocols, layer 4, major protocols, TCP or UDP used for communication, internet, layer 3 protocol, and some lower level stuff, layer 2, layer 1 in network interface. But what is basically in a nutshell happening, let's just go to this picture, maybe save it, save image as on my desktop. So in order for any application to communicate, the data will be broken down into chunks. So the data will be broken down into chunks. Those chunks will be sent separately, encapsulated in multiple headers. Before any communication happens, there's a protocol at layer 4 chosen by the application developer, and it's either going to be TCP or UDP. More on those in the blog, but in a nutshell, TCP is a connection-oriented protocol which does take care of resending, retransmitting something that is lost or broken in the process. Now, what happens is at the first stage, there's something called three-way handshake taking place. So the application, which initiates the client, which initiates the session with the server, is going to ask permission to connect to the application on the other end. So it's going to be sending synchronized flag saying, hey, my application wants to talk to your application. How about that? The server is, if okay with that, is going to respond with the TCP information saying, yes, I'm good. So this is going to be acknowledgement. But my application wants to communicate with your client application as well, and it's going to send a SYN flag as well. So it's called SYN-ACK reply. And finally, that needs to be acknowledged by the client, the initiator of a session. That's why we call this three-way handshake, because there are three packets exchanged before the actual data from the application come in. Once it happens, though, the data will be broken down into smaller chunks, and each chunk will be encapsulated first in the TCP layer 4 header, if TCP was chosen. Then that is going to go down to the layer 3 process on the sender, and the layer 3 header, IP header, will be attached to it. And then it's going to be ultimately encapsulated in Ethernet frame with the layer 2 header. So all these headers will be inside that layer 2 header. Now the bridges, or switches I should say these days, will only be looking at the layer 2 header. The routers will be looking at the layer 2 and layer 3 headers, and the servers and clients will look at all of them. So let's just see how this works in practice, and I'm going to use Wireshark for that. So what I'm going to do to actually show this encapsulation process is to capture the packets between my computer here, which is my Linux machine, and I'm going to be doing SSH to my Raspberry Pi. The address of that device is 192.168.0.254. Before I hit enter, I'm going to enable Wireshark, and I'm going to go to capture and options. In the options, I'm going to only focus on capturing communication with the host 192.168.0.254. So going towards that host or coming back from that host. This will just save me on capturing any other packets coming through my computer. So if I do that, nothing shows up until I hit enter. So let's go for ifconfig and let's see what the MAC address and IP address are. So IP address is my 192.168.0.254. That's the destination for the session. And that is the Ethernet address of this guy. So it's 8D6A. Let's remember that. Now, if I exit from that, terminate session, I'm gonna stop my capturing. I'm gonna save this capture for later on my desktop maybe. So let's go to my desktop and say SSH capture example. And we're gonna analyze it in just a second. So let's go back to the beginning of this. So what happened actually in the background? The first thing that happens is the computer sender client, my laptop, ifconfig, has IP address assigned to it, which is 192.168.0.12, and it has a burnt-in address in the wireless adapter here, which is 2051 at the end. Now, in order for this to communicate, the application must realize whether the host recipient is on the same subnet as me or not. If it's on the same subnet, the router is not used. If it's not on the same subnet, we need to send that information at the layer 2 to the router for processing. Since this is not the case, and we'll get into that later, we will be sending information from the computer, my client, to the server that are on the same subnet. For that to communicate, my sender needs to know what is the MAC address for the IP destination 192.168.0.254. And it is actually, once learned, it is stored for some time in ARP cache of the sender. By the way, the receiver, upon receiving packets, will do the same thing for me, the sender, and my MAC address. It will remember who is sending at the layer 3 IP and will remember what the MAC address of a sender is as well. So it works both ways. So I have here right now Art-A and grep for Tron. That's just gonna be my destination, my Raspberry Pi server, and this IP address uses that MAC address. But how did my computer obtain that? Well, the answer to the question is actually in the capture, my Wireshark capture. The first thing my computer did was sending something called broadcast. Broadcast is a communication from one computer to everyone on the network. And there's a specially designed MAC address for that at the layer 2, which represents everyone. So let's just see more or less what it is. And in here I can say, maybe let's smoosh it down. There's an envelope header, layer 2 header, which is represented here as a layer 2 header here, or maybe here it's a larger layer 2 header. And that header has certain fields in it. Let's see what those fields are. There's a destination MAC address, there's a source MAC address, and what is the communication inside that envelope. So destination MAC address for the question is this: FFFF all Fs. Sender is my laptop 2051. What it is sending to everyone? Well, inside this envelope, inside this header, there's the ARP request, which is the code 0x0806. And that ARP request is right here. What's in it? In it we find, hey, this is me, sender, and this is my MAC address, 74DFBF442051. My IP address, by the way, is this one, 192.168.0.12. I am looking for MAC address of a host with IP address 192.168.0.254. I have no knowledge at the moment of what that MAC address is. So that is sent as a broadcast, meaning sender 2051 to everyone. Listen up. Who has 192.168.0.254? Please respond to me. Tell me your MAC address. Upon receiving that, all devices in my network said, okay, this is not me, this is not me, this is me. And my Raspberry Pi says, oh, that's me. I am now 192.168.0.254. So what it does, it sends the reply back directly to me, not everyone, because it already knows who's asking the question. So it's sending information, also Ethernet header, and this is me, B827EBF3AD6A, responding to the laptop that is the recipient now, who sent the query, the question. Inside we have ARP reply, code 0806, so that's ARP protocol. And in ARP reply we see my name is B827EBF3AD6A. This is my IP address, 192.168.0.254. I'm responding to this guy, MAC address 2051, which is my laptop, who sent the query to begin with, and with this IP address. So at that point, my sender, my client, knows what the MAC address of the recipient is. So it can now communicate. What happens next is a three-way handshake. So that is represented here in this capture packet 3, 4, and 5. Let's see what happens first. So at this point, application cannot communicate because SSH uses TCP, and for this, TCP protocol has to establish communication between applications. So this is where this three-way handshake I mentioned before is happening. So at the layer 4, there's a header created, and that header is represented here, layer 4 header. Before data actually is being sent, forget about the data, it's not being sent at the moment, it's just an empty layer 3 header, which is going to be encapsulated in IP and in Ethernet. So that encapsulation actually is visible here. We have this TCP header, transport protocol, in which this system uses the source port and destination port. So let's go back to initiation of the session, the SYN packet here, packet number 3. My sender is creating a TCP header in which it chooses random port above 1023 called ephemeral port, and it has to be above 1000 well-known ports at 1023. It's actually 50,008, and in the destination port it indicates that the application process, which will be using this source port in a moment, will need to talk to the application well-known port SSH22. What it sends in its flags, again, this is a long story, but it sends one flag which is called SYN, saying, hey, my application, which will be used from port 50,008, wants to talk to SSH port 22, and it tries to establish session, sends the kind of like an invitation, hey, can I talk to you? What comes back? And this is, by the way, encapsulated in IP header, which is source IP 192.168.0.12 and destination IP 254. Inside, we know there's going to be TCP protocol inside this envelope, and this is encoded with this protocol TCP number 6. So the recipient knows upon receiving this IP that the recipient of that is the TCP, not UDP. And that is further encapsulated in Ethernet frame with the source MAC address of my laptop 2051, and destination we already know based on ARP request, ARP reply, which is 8D6A. That is represented here. We're sending this right here, all of it without the data at the moment. Now what happens next? The recipient says, okay, cool, and sends something like this. In the TCP, so it gets to first layer 2, the recipient checks, am I the destination MAC address? Oh, that's me, 2051, that's me. Okay, so what's inside? It's IP protocol. The code is 0800. It rips this envelope apart, puts this in the bin, and sends the information to the protocol IP. So what is sent to the IP is this. And it says, okay, destination is 012, and that's me. This is the sender. Keeps that on the side as information. What's inside? It's TCP. Removes that header. So remove the encapsulates the header. Layer 2 was removed. Layer 3 now is removed here. And we send the information to the layer 4 TCP protocol for processing. So what happens here is layer 4 says, okay, I am talking back from port 22 you are knocking on to port 50,008. And I'm saying, acknowledge, yes, I want to talk to you. My application will be ready to receive information from you in a second. I acknowledge the session has been established. But I need my application, port 22 SSH, to your client application, which now operates on port 50,008, I need the communication in that direction as well. So I'm sending my own SYN packet. So this is known as SYN ACK reply. And that needs to be acknowledged by the recipient, which is now my laptop who initiated the session. So this is the packet number 4, finally sending the same stuff at the layer 4. It acknowledges the SYN flag received from the Raspberry Pi. It knows that the source is me, destination is Raspberry Pi right here, and it knows what the MAC addresses of the sender and the receiver are. So it goes back, and at this point the application layer can kick in and SSH begins its magic. So at this point, and only at this point, can we use that data and encapsulate in the exact same process like that. Only there's more stuff involved because we need to kind of trace what was sent, what was received with acknowledgement and numbers here in the TCP header. So when you look at this transmission protocol, now we have sequence numbers, acknowledge numbers. There's not enough time here to discuss that, but that's a topic on its own. So that communication is basically happening every time our computers talk. The reason I'm talking about this, because in the next video I want to try to get into switching, and switches only understand how to read this small Ethernet header with the source, destination, MAC addresses, and based on those, the switches will make forwarding decisions in terms of how the packets are transmitted.